Tonight, we'll embark on a journey that will stretch your imagination to its very limits. We'll travel from the familiar confines of your immediate surroundings to distances so vast that numbers themselves begin to lose their meaning. We'll explore structures so large that entire galaxies become mere dots of light, and contemplate scales so enormous that our entire observable universe might be nothing more than a single bubble in an infinite cosmic foam. Imagine standing on a beach at sunset, holding a single grain of sand between your fingers. Feel its weight. Examine its tiny crystalline structure, perhaps formed from quartz worn smooth by countless waves over millions of years. Such a tiny, seemingly insignificant speck. Now, consider this mind-bending fact. There are more stars in the observable universe than there are grains of sand on every beach, in every desert, in every sandbox, on our entire planet Earth. But that comparison, staggering as it is, barely scratches the surface of cosmic scale. If we were to represent our entire observable universe, that sphere of space containing everything we can possibly see or detect, as that single grain of sand in your fingers, then the actual full universe might be as vast as planet Earth itself, or perhaps larger than our solar system, or maybe even infinite beyond all comprehension. We are not just small, we are so monumentally, breathtakingly, incomprehensibly small that our minds, evolved to navigate African savannas and social relationships, struggle with concepts that dwarf our very capacity for understanding. Consider the audacity of what we're attempting tonight. Here you sit, a collection of atoms barely 5.5 feet tall on average, living on a rock that's 7,126 miles across, contemplating structures that span hundreds of millions of light years. It would be like a bacterium attempting to understand the geography of Earth, or a mayfly trying to comprehend geological time. Yet somehow, impossibly, we've managed to do exactly that. But here's what's truly remarkable about our infinitesimal existence. Despite being less than a microscopic dot in the cosmic tapestry, despite existing for a mere eye blink in cosmic time, we have the extraordinary ability to measure, understand, and contemplate the very universe that contains us. Every calculation you'll hear tonight, every measurement that reveals our cosmic address, every discovery that illuminates the universe's vast architecture was made by beings no larger than you, living on a world that's essentially invisible from even our nearest stellar neighbors. The photons entering your eyes right now, allowing you to see these words, have traveled at 186,282 miles per second from their source. If those photons came from the sun, they've journeyed for 8 minutes and 20 seconds across 93 million miles of space. If they originated from the nearest star beyond our sun, they've been travelling for over 4 years. And if they came from the most distant galaxies we can observe, they began their journey when the universe was young, having travelled for nearly 13.8 billion years to reach you in this moment. For millennia, humans have gazed upward and wondered about the nature of existence itself. Ancient civilizations created elaborate mythologies to explain the dome of stars above their heads, imagining crystalline spheres carrying celestial bodies around a central Earth, divine realms just beyond the reach of mortal understanding. The Babylonians thought the stars were holes in the sky through which divine light shone. The Greeks envisioned a geocentric cosmos with Earth at its center, surrounded by nested spheres carrying the moon, sun, planets, and stars. These weren't primitive superstitions born of ignorance. They were sophisticated attempts to understand the cosmos using the best observational tools and theoretical frameworks available. The ancient astronomers were remarkable observers who tracked planetary motions, predicted eclipses, and created calendars that governed agricultural and religious life. They understood that the cosmos was larger than their immediate experience, but they could never have imagined the true scale we've discovered. Medieval Islamic astronomers like al-Battani and al-Biruni made precise measurements of Earth's size and the distances to the Moon and Sun. They calculated Earth's circumference to within a few % of the modern value, and estimated the distance to the Moon with remarkable accuracy. Yet even these sophisticated observers thought the sphere of fixed stars was perhaps a few tens of millions of miles away. Vast by human standards, but laughably small compared to what we now know, the Renaissance brought the first hints of cosmic vastness. When Galileo turned his telescope skyward in 1609, he discovered that the Milky Way, that faint band of light crossing the night sky, was composed of countless individual stars. Each point of light he observed represented a sun potentially like our own, scattered across distances that began to challenge human comprehension. As telescopes improved, so did our appreciation of cosmic scale. In the 18th century, astronomers like William Herschel began to map the distribution of stars and realized that our sun was part of a vast stellar system. They began to grasp that we lived within what we now call a galaxy, though they still believed this galaxy constituted the entire universe. The early 20th century brought revolutionary discoveries. In 1925, Edwin Hubble used the 100-inch telescope at Mount Wilson Observatory to observe individual stars in what we now know is the Andromeda Galaxy. By studying the brightness variations of Cepheid variable stars, he proved that Andromeda was far too distant to be part of our own galaxy. In a single observation, Hubble expanded the known universe by a factor of millions, revealing that our Milky Way was just one island of stars among countless others scattered across unimaginable distances. But Hubble's discoveries were just the beginning. His subsequent observations revealed that these island universes were moving away from us, and the more distant they were, the faster they receded. This observation led to the revolutionary understanding that space itself is expanding, carrying galaxies apart like dots on an inflating balloon. The universe wasn't just vast and static, it was growing larger every moment. How wonderfully, humbly wrong our ancestors were about cosmic scale. What we've discovered makes every ancient mythology seem quaint by comparison. The truth is far more magnificent and terrifying than any human imagination could have conjured. Our universe is not just large, it's so incomprehensibly vast that even our largest numbers begin to lose meaning, where distances are measured in units that themselves strain comprehension. Let's begin this journey by establishing our cosmic address with mathematical precision, starting with what we can see and touch, gradually expanding outward until we reach the very limits of the knowable universe. This isn't just an exercise in astronomy, it's a profound meditation on our place in existence itself. You are sitting on Earth, a nearly spherical world with an equatorial diameter of 7,226 miles and a polar diameter of 7,900 miles. Our planet is slightly oblate, flattened at the poles due to its rotation, spinning once every 23 hours, 56 minutes, and 4 seconds relative to the stars. That's our starting point, our home base in this cosmic exploration, a world with a surface area of 197 million square miles, 71% of which is covered by oceans containing 1.37 billion cubic kilometers of water. To truly appreciate Earth's size, consider that you could walk around our planet's equator in about 9 months if you maintained a steady pace of 3 miles per hour for 8 hours each day. The deepest point on Earth's surface, the Challenger Deep in the Mariana Trench, lies 6.83 miles below sea level. Mount Everest rises 5.5 miles above sea level. The total vertical relief of our world spans just 12.3 miles, a distance you could drive in about 15 minutes. Yet within this thin shell at the surface of a rocky ball, every human story has unfolded. Earth's gravitational field extends infinitely into space, though it weakens with distance according to the inverse square law. The International Space Station orbits just 254 miles above Earth's surface, still well within our planet's gravitational embrace. At this altitude, Earth fills most of an astronaut's field of view, a breathtaking blue marble suspended in the cosmic dark. From the Moon's distance, 238,855 miles away, Earth appears as a bright blue-white dot, still easily visible but no longer dominating the sky. If Earth were the size of a marble, about half an inch across, the Moon would be a small pebble about 1/8 inch in diameter, orbiting roughly 2.5 feet, about 30 inches, away. This Earth-Moon system represents humanity's complete sphere of direct experience. Every human who has ever lived has remained within this tiny bubble of space, with only 24 individuals having ventured as far as the Moon's vicinity. But our Earth-Moon system is just the beginning of our solar neighborhood. We orbit the Sun at an average distance of 92,955,807 miles, a distance so fundamental to astronomy that we use it as a unit of measurement called the astronomical unit, or AU. Light from the Sun takes exactly 8 minutes and 20 seconds to reach Earth, meaning that when you look at the Sun, though you shouldn't look directly at it, you're seeing it as it was more than 8 minutes ago. Our solar system, that collection of planets, moons, asteroids and comets gravitationally bound to our Sun, extends far beyond the orbit of Neptune, the most distant major planet at 30 AU from the Sun. The dwarf planet Pluto, despite its demotion from full planetary status, orbits between 29.7 and 49.3 AU from the Sun in its elliptical path. But even Pluto isn't at the edge of our solar system. The Kuiper Belt, a region of icy bodies beyond Neptune's orbit, extends from about 30 to 50 AU from the Sun. Beyond this lies the scattered disk, reaching perhaps 100 AU from the Sun, populated by objects like the dwarf planet Eris. But the true boundary of our solar system lies much farther out, in a theoretical region called the Oort cloud. The Oort cloud, named after Dutch astronomer Jan Oort, who first proposed its existence, is thought to be a vast spherical shell of icy objects surrounding our solar system at distances between 2,000 and 100,000 AU from the Sun. This is where long-period comets originate, taking hundreds or thousands of years to complete their orbits. At its farthest extent, 100,000 AU, about 1.6 light-years, the Oort cloud reaches roughly 1/3 of the way to the nearest star. If we shrink our solar system so that the Sun becomes the size of a basketball sitting at center court, Earth would be a tiny bead, barely visible, located about 85 feet away. This distance is accurate within a few feet. Jupiter would sit roughly 440 feet away, about 1.5 football fields, not merely at the opposite end of a single court. Neptune would be nearly half a mile away, around 0.5 miles, several city blocks depending on the city. And the edge of our solar system, the outer boundary of the hypothetical Oort cloud, would extend roughly 1,600 miles in every direction, Earlier analogies sometimes gave 3,000, encompassing an area still larger than many countries. All of these are approximate, but they convey the true emptiness and scale. This is the small, intimate corner of space that humanity has called home for its entire existence. Our fastest spacecraft, Voyager 1, launched in 1977, has travelled for over 45 years and has only just left our solar system, entering the interstellar medium at a distance of over 162 AU from the Sun as of 2025. At its current speed of about 38,000 miles per hour, Voyager 1 would still need on the order of 70,000 plus years to travel the distance to the nearest star. And here we encounter the first mind-bending leap in cosmic scale. The nearest star to our Sun, Proxima Centauri, is 4.4 light-years away. A light-year, the distance light travels in 1 Earth year, equals approximately 5.88 trillion miles, or 63,241 AU. Using our basketball-sized Sun model, Proxima Centauri would be another basketball located 16,000 miles away, about 2,000 miles farther than the distance from New York to Tokyo. But Proxima Centauri is not just any star. It's a red dwarf, much smaller and dimmer than our Sun, with about 12% of the Sun's mass and only 0.17% of its luminosity. If you were somehow transported to Earth's distance from Proxima Centauri, that star would appear as a dim red dot, providing about as much light as our Sun does from the distance of Jupiter. Any planets orbiting in Proxima Centauri's habitable zone would need to be much closer to their star than Earth is to the Sun, completing their years in just a few Earth days. Proxima Centauri is part of a triple star system called Alpha Centauri, which includes 2 Sun-like stars orbiting each other, Alpha Centauri A and Alpha Centauri B. These 3 stars represent our closest stellar neighbours, isolated from us by a gulf of space so vast that it defies everyday comprehension. Imagine 2 basketballs separated by 16,000 miles of empty space, and you begin to grasp the profound loneliness of stars in our galactic neighbourhood. The next nearest stars are part of Barnard's star system at 596 light-years, Wolf 359 at 786 light-years, and Lalande 21185 at 829 light-years. These distances represent the immediate stellar neighbourhood of our Sun, a region astronomers call the local bubble or local cavity. Within 15 light-years of Earth, there are approximately 45 known star systems, many containing multiple stars or having planetary companions. But even this local stellar neighbourhood is just a tiny corner of a much larger structure. Our Sun, along with approximately 200 to 400 billion other stars, forms a galaxy we call the Milky Way. The exact number of stars in our galaxy remains uncertain because many are too dim to detect directly, hidden by intervening dust, or exist as part of multiple star systems that are difficult to resolve with current telescopes. The Milky Way is a barred spiral galaxy, meaning it has a central bar-shaped structure from which spiral arms extend outward. Our galaxy measures approximately 105,700 light-years in diameter, though recent observations suggest it might be even larger, possibly reaching 200,000 light-years across if we include its sparse outer halo of stars. The galactic disk itself is relatively thin, with most stars confined to a region about 1,000 light-years thick, giving our galaxy the proportions of a dinner plate. To truly appreciate the Milky Way's scale, consider this. If you could travel at the speed of light itself, 186,282 miles per second, it would take you 150,700 years to cross from one side of our galaxy to the other. Light that left the far edge of our galaxy when the first anatomically modern humans were developing language, creating the first cave paintings and beginning to spread across continents is only just now reaching the opposite side of our galactic home. Our entire species, from the first stirrings of human consciousness to our current technological civilization, has existed for less time than it takes light to cross our home galaxy. The rise and fall of entire ice ages, the evolution of agriculture, the birth of writing, the entire span of recorded history. All of these profound chapters in human development represent just a fraction of the time required for light to traverse our galactic neighborhood. Within this vast galactic disk, our solar system occupies what astronomers consider an unremarkable position, located approximately 26,000 to 28,000 light-years from the galactic center. We reside in what's called the Orion Arm or Local Arm, a minor spiral structure between two major arms of our galaxy. The Sagittarius Arm, also known as Sagittarius Carina Arm, lying closer to the galactic center, and the Perseus Arm extending farther out toward the galaxy's edge. Our position in this galactic suburb is actually quite fortunate for the development of life. The galactic center, while spectacular, is a violent place dominated by a supermassive black hole called Sagittarius A, pronounced Sagittarius A star, which contains the mass of about 415 million suns compressed into a region smaller than Mercury's orbit. The central regions of galaxies are also rich in high-energy radiation and frequent stellar collisions, conditions that would make the long-term stability necessary for biological evolution extremely difficult. Too far out toward the galactic edge, and there wouldn't be enough heavy elements, what astronomers call metals, to form rocky planets like Earth. The outer reaches of galaxies are populated primarily by older metal-poor stars that formed before multiple generations of stellar nucleosynthesis had enriched the galaxy with carbon, oxygen, silicon, and iron. Our position in the galaxy's habitable zone provides the perfect balance, far enough from the center to avoid catastrophic events, close enough to benefit from stellar recycling of heavy elements. We orbit this galactic center at an average speed of approximately 514,000 miles per hour, or about 143 miles per second. Despite this tremendous velocity, our orbital period around the galaxy is so long that astronomers call it a galactic year. One complete orbit takes approximately 225 to 250 million Earth years. The last time our solar system was in its current position relative to the galactic center, dinosaurs had not yet appeared on Earth. The previous time we completed this cosmic circuit, the supercontinent Pangaea was forming, and the first reptiles were evolving from amphibians. Since Earth formed 4.54 billion years ago, our solar system has completed only about 20 galactic orbits. The entire history of complex multicellular life on Earth spans just the most recent galactic orbit. Human civilization, from the first agricultural settlements to our current spacefaring capability, represents less than 1/10,000,000th of a galactic year. The structure of our galaxy tells a story of cosmic evolution spanning billions of years. The oldest stellar populations and globular clusters associated with the Milky Way trace back to more than 13 billion years ago, while the thin disk, including the Sun's region, assembled later over roughly the past 8 to 10 billion years. Its central bulge contains primarily old, metal-poor stars that formed during the galaxy's youth, when the universe contained much less of the heavy elements necessary for planet formation. The spiral arms, including our own Orion Arm, are regions of active star formation, where giant molecular clouds collapse under their own gravity to create new stellar nurseries. These arms aren't fixed structures like the spokes of a wheel. Instead, They're density waves that rotate around the galaxy at a different speed than the stars themselves. As our solar system orbits the galactic center, we periodically move into and out of these spiral arms, potentially affecting Earth's climate and the rate of mass extinctions through increased cosmic ray exposure and gravitational perturbations of the Oort cloud. The disk of our galaxy is embedded within a much larger, roughly spherical structure called the galactic halo, which extends perhaps 200,000 light-years from the galactic center. This halo is populated by globular clusters, ancient, densely packed collections of stars that formed during the galaxy's earliest epochs, and vast amounts of dark matter, an invisible substance that outweighs all the visible matter in our galaxy by approximately 10 to 1. Recent discoveries have revealed that our galaxy is even more complex than previously imagined. The Gaia Space Telescope, launched by the European Space Agency, has mapped the positions and motions of over 1.7 billion stars with unprecedented precision. These observations have revealed that our galaxy has a violent history of collisions and mergers with smaller galaxies. We can still see the remnants of these ancient catastrophes in streams of stars that have been torn from their original galaxies and now orbit as part of our Milky Way's extended halo. One of the most significant of these merger events involved a galaxy astronomers call Gaia Enceladus, which collided with the Milky Way approximately 10 billion years ago. This collision was so massive that it fundamentally altered our galaxy's structure, helping to create the thick disk component we observe today and contributing countless stars to our galactic halo. The discovery of this ancient merger has revolutionized our understanding of galactic evolution, showing that even massive spiral galaxies like our own are built up through the accumulation and collision of smaller structures over cosmic time. But our galaxy, vast as it is just one island of stars in a much larger cosmic ocean that stretches beyond imagination. The nearest large galaxy to our own is Andromeda, officially designated M31 in Charles Messier's catalogue of fuzzy objects that might be mistaken for comets. Andromeda lies at a distance of approximately 2.537 million light-years from Earth, making it the most distant object visible to the naked eye under dark skies. The Andromeda Galaxy is truly magnificent in scale and structure. It contains approximately 1 trillion stars, roughly 2.5 times as many as our Milky Way, and spans about 220,000 light-years in diameter, making it significantly larger than our home galaxy. Its mass is estimated at 1.5 trillion times that of our Sun, compared to the Milky Way's estimated mass of 1.2 trillion solar masses. If you could see Andromeda's full extent in the night sky, it would appear about 6 times larger than the full moon, covering an area roughly the size of your outstretched hand held at arm's length. Despite the immense distance separating us from Andromeda, this galaxy is actually approaching the Milky Way at a speed of about 250,000 miles per hour due to mutual gravitational attraction. In approximately 4.5 billion years, these two galactic giants will collide and merge in a cosmic dance that will fundamentally reshape the local universe. Computer simulations of this Milky-Meter collision show that while individual star systems like our solar system are unlikely to experience direct collisions due to the vast spaces between stars, the gravitational disruption will dramatically alter both galaxies' structures. During the collision process, which will unfold over several billion years, both galaxies will be stretched and distorted by tidal forces. Star formation will be triggered on a massive scale as gas clouds collide and compress. The supermassive black holes at the centers of both galaxies, Sagittarius A in the Milky Way, and the even more massive black hole at Andromeda's core, will eventually spiral together and merge, creating gravitational waves that will ripple through space-time itself. The final result will be a giant elliptical galaxy containing the combined mass of both original galaxies. Our Sun, if it still exists as a main sequence star at that time, will likely find itself in a much different galactic environment, possibly ejected to the outer reaches of the merged galaxy, or even flung into intergalactic space entirely. But don't worry. This cosmic collision is still far in the future, long after our Sun will have evolved into a white dwarf star. The Milky Way and Andromeda, along with over 100 known smaller galaxies, form what astronomers call the local group. This gravitationally bound collection of galaxies spans approximately 10 million light-years across. Though the exact boundaries are somewhat fuzzy, as smaller galaxies gradually join or leave the group over cosmic time. Most of the smaller galaxies in our local group are dwarf galaxies, containing anywhere from a few million to a few billion stars, tiny compared to giants like Andromeda and the Milky Way, but still representing vast collections of stellar systems. Some of these dwarf galaxies are satellites of our own Milky Way, orbiting our galaxy like cosmic moons. The most prominent are the large and small Magellanic Clouds, visible to the naked eye from Earth's southern hemisphere as fuzzy patches of light that indigenous peoples of the southern hemisphere incorporated into their mythologies for thousands of years. The Large Magellanic Cloud lies about 158,000 light-years from Earth, and contains on the order of 30 billion stars. Earlier rough estimates cited euro 20 billion, while the Small Magellanic Cloud, at 200,000 light-years distance, holds about 3 billion stars. These Magellanic Clouds are not just passive satellites. They're being gradually torn apart by the Milky Way's gravitational field, creating streams of stars and gas called the Magellanic Stream that stretches across more than 200 degrees of the sky, as seen from Earth. This cosmic archaeology reveals the dynamic nature of galactic interactions, and reminds us that even over the vast scales of galactic evolution, change is constant. Other notable members of the local group include the Triangulum Galaxy, M33, a smaller spiral galaxy about 3 million light-years away containing roughly 40 billion stars. There's also a collection of dwarf elliptical and spheroidal galaxies with names like Draco, Ursa Minor, Sculptor, and Fornax, each representing a gravitationally bound system of millions to billions of stars, yet appearing as mere smudges of light even in powerful telescopes. The local group itself is not a static collection. Computer simulations show that over the next several billion years, the gravitational interactions between member galaxies will result in most of the smaller galaxies being absorbed by either the Milky Way or Andromeda before these two giants eventually merge. The local group represents a preview of cosmic evolution on the largest scales, where structure grows through hierarchical merging, with smaller objects being incorporated into ever larger systems. But even the local group, spanning 10 million light-years and containing dozens of galaxies, is a relatively small structure in the cosmic hierarchy. Galaxy groups and clusters are themselves organized into even larger structures that boggle the mind with their sheer scale. Our local group is part of what astronomers call the Virgo supercluster, also known as the local supercluster, a vast gravitationally influenced region that contains at least 100 galaxy clusters and groups spread across approximately 110 million light-years. To put this in perspective, if our local group were the size of a dinner plate, the Virgo supercluster would be larger than a football stadium. The Virgo supercluster contains on the order of many tens of thousands of galaxies. Earlier rough tallies quoted a figure of 47,000, with a total mass roughly 10-15 times that of our Sun. That's a 1 followed by 15 zeros times the mass of our star. This incomprehensible mass is dominated by dark matter, the mysterious invisible substance that outweighs visible matter by approximately 5-1 throughout the universe. At the heart of this supercluster lies the Virgo cluster, a massive collection of over 300 galaxies located about 54 million light-years from Earth. The Virgo cluster is dominated by giant elliptical galaxies, including M87, a supergiant elliptical galaxy that contains over 1 trillion stars and hosts one of the most massive black holes known to science. This black hole, with a mass 6, 5 billion times that of our Sun, was the first black hole ever directly imaged by the Event Horizon Telescope in 2019, producing the iconic photograph that showed the shadow of a black hole silhouetted against its glowing accretion disk. The gravitational influence of the Virgo cluster affects the motion of galaxies across hundreds of millions of light-years, including our own local group. We experience a peculiar velocity component toward Virgo of a few hundred kilometers per second, roughly 300 km/s, though this cosmic attraction is so gradual that it will take far longer than the current age of the universe for any dramatic restructuring of our local neighborhood. The Virgo supercluster itself exhibits a complex web-like structure. Galaxies and galaxy groups are not randomly distributed, but are organized into filaments and sheets separated by vast voids containing very few galaxies. This cosmic web structure emerged from the initial tiny fluctuations in density that existed in the early universe, amplified over billions of years by gravitational attraction and the influence of dark matter. Recent discoveries have revealed that even superclusters are part of larger structures that span truly mind-boggling distances. In 2014, astronomers identified that our Virgo supercluster is actually just one component of an even more massive structure called Laniakea, which means immense heaven in Hawaiian. The name is profoundly appropriate for a structure of such staggering scale. Laniakea contains approximately 100,000 galaxies spread across 520 million light-years, with a total mass of about 1017 solar masses. To comprehend this scale, imagine shrinking everything down so that our entire Milky Way galaxy, with its 200 billion stars spanning 100,000 light-years, becomes the size of a grain of sand. Even at this drastically reduced scale, Laniakea would still stretch about 50 miles across, larger than many metropolitan areas on Earth. The discovery of Laniakea was made possible by mapping the peculiar velocities of thousands of galaxies, the component of their motion that deviates from the general expansion of the universe. By studying how galaxies move relative to the cosmic expansion, astronomers can trace the gravitational influence of massive structures and map the cosmic web in 3 dimensions. Laniakea represents the basin of attraction that influences the motion of all galaxies within its boundaries, including our own local group. At the center of Laniakea lies the Great Attractor, a gravitational anomaly that appears to be drawing our local group and thousands of other galaxies toward a region of space in the direction of the constellations Hydra and Centaurus. The Great Attractor was first discovered in the 1970s when astronomers noticed that our local group was moving through space at about 600 kilometers per second relative to the cosmic microwave background radiation, the afterglow of the Big Bang itself. For decades, the nature of the Great Attractor remained mysterious because it lies in the zone of avoidance, a region of sky obscured by the dense stellar fields and interstellar dust of our own Milky Way. Using infrared and radio telescopes that can peer through this dust, astronomers have revealed that the Great Attractor is associated with the Norma Cluster and other massive galaxy clusters, but the full extent of this gravitational influence remains an active area of research. But we're still not done climbing the ladder of cosmic scale. Laniakea and other superclusters are organized into an even larger structure that astronomers call the cosmic web, perhaps the most beautiful and organized pattern in the entire universe. This vast network of galaxy filaments separated by enormous voids resembles a three-dimensional spiderweb spanning billions of light years, creating the largest known structures in the cosmos. The cosmic web consists of dense filaments where galaxies cluster together like beads on string, connected by thinner threads of dark matter and ordinary matter, all surrounding vast empty regions called cosmic voids. These filaments can stretch for hundreds of millions of light years, creating highways of matter that connect distant regions of the universe. The intersections where multiple filaments meet often host the most massive galaxy clusters, sitting like cosmic cities at the junctions of this celestial interstate system. The cosmic voids that separate these filaments are among the most empty places in the universe. These voids can be hundreds of millions of light years across, containing very low galaxy densities, typically just a small handful of faint dwarfs plus dark matter. The Buta's void, about 330 million light-years in diameter, still contains an estimated few dozen galaxies, roughly 60 identified, which is extremely underdense but not literally empty. If Earth were located near its centre, the night sky would have far fewer bright galaxies, and modern extragalactic astronomy would likely have advanced more slowly. These voids are not truly empty. They contain dark matter, scattered gas atoms, and occasional dwarf galaxies, but their density is less than 10% of the universe's average density. If you were somehow transported to the centre of a cosmic void, the night sky would be almost completely black, with perhaps only a handful of extremely distant faint galaxies visible even with the most powerful telescopes. The cosmic web formed in the early universe as dark matter collapsed under its own gravity, creating the scaffolding upon which normal matter could accumulate into the first stars and galaxies. Computer simulations of structure formation, using our best understanding of dark matter and dark energy, reproduce the cosmic web pattern observed in large galaxy surveys with remarkable accuracy. This agreement between theory and observation represents one of the great triumphs of modern cosmology. The process of structure formation begins with tiny quantum fluctuations that existed in the first moments after the Big Bang. These microscopic variations in density were stretched to cosmic proportions during a period of exponential expansion called cosmic inflation, which occurred in the first tiny fraction of a second of the universe's existence. Over billions of years, gravity amplified these initial fluctuations, causing regions of slightly higher density to attract more matter and grow, while less dense regions became increasingly empty. The cosmic web we observe today is the result of nearly 13.8 billion years of gravitational evolution, shaped by the competing influences of gravity trying to pull matter together and the expansion of space trying to pull it apart. The pattern is further complicated by dark energy, the mysterious force causing the universe's expansion to accelerate, which affects structure formation on the larger scales. Recent surveys have mapped the cosmic web in unprecedented detail, The Sloan Digital Sky Survey has catalogued the positions of millions of galaxies, revealing the filamentary structure across billions of light-years. The 2DF Galaxy Redshift Survey mapped over 220,000 galaxies, creating three-dimensional maps that clearly show the cosmic web's intricate architecture. These surveys have revealed that on the largest scales, the universe is remarkably homogeneous. The cosmic web looks statistically the same, regardless of which direction you look or which region of space you examine. This homogeneity is both expected and puzzling. It's expected because the cosmic microwave background radiation, the afterglow of the Big Bang, shows that the early universe was extremely smooth, with temperature variations of only about 1 part in 100,000, tens to a few hundred microkelvin, ruled 1005 degrees C, across the entire observable universe. It's puzzling because regions of the early universe that are now separated by billions of light-years appear to have the same temperature and properties, even though they couldn't have been in causal contact, given the finite speed of light and the age of the universe. This horizon problem is one of several cosmological puzzles solved by the theory of cosmic inflation. If the universe underwent a brief period of exponential expansion in its earliest moments, regions that are now separated by vast distances were once in close contact, allowing them to reach thermal equilibrium before inflation stretched them apart. Inflation also explains the nearly perfect flatness of space and the absence of certain exotic particles predicted by particle physics theories. The cosmic web structure extends to the very limits of our observational capabilities. The most distant galaxies we can observe existed when the universe was less than 1 billion years old, and they already show signs of being organized into the filamentary structures that characterize the cosmic web. This suggests that the basic architecture of the universe was established very early in cosmic history. Now we approach the boundary of what we can observe, the ultimate horizon that defines the limits of human knowledge about the cosmos. Due to the finite speed of light and the finite age of the universe, there exists a fundamental limit to how far we can see into space. This boundary, called the edge of the observable universe, represents not just a limitation of our telescopes, but a fundamental constraint imposed by the laws of physics themselves. Light from the most distant objects we can observe has been travelling toward us for 13.8 billion years, essentially since the moment the universe became transparent to light after the Big Bang. Before this epoch, called the last scattering surface, the universe was filled with a hot, dense plasma that was opaque to electromagnetic radiation. No telescope, no matter how powerful, can see beyond this cosmic fog that lifted when the universe was only 380,000 years old. However, due to the expansion of space itself, a phenomenon that affects the very fabric of space-time, objects at the edge of the observable universe are now much farther away than the simple calculation of 13.8 billion light-years might suggest. The cosmic expansion has been stretching space during the entire journey of that ancient light, carrying those distant sources ever farther from us as their photons travelled through the expanding universe toward Earth. When we account for this cosmic expansion, the most distant observable objects are now approximately 46.5 billion light-years away from us. This gives our observable universe a diameter of about 93 billion light-years, creating a sphere of observability that contains everything we can possibly know about through direct observation. This observable universe is not centered on Earth because Earth is special, but rather because we can only observe light that has had time to reach us since the Big Bang occurred. Every point in the universe has its own observable universe, a sphere of the same size centered on that location. An alien astronomer on a planet in the Andromeda Galaxy would see a slightly different observable universe, one that overlaps substantially with ours, but includes some regions we cannot see while missing others that are visible to us. The total observable universe from any location contains the same volume of space and the same amount of information about cosmic history. Within this observable sphere, earlier extrapolations, pre-JWST, suggested there could be up to about 2 trillion galaxies using Hubble Deep Field data and statistical corrections. Newer JWST-informed analyses point to a lower figure, likely several hundred billion, perhaps 200-400 billion galaxies, though the precise number remains uncertain. Each of these galaxies contains anywhere from millions to trillions of stars, leading to a total stellar population plausibly in the 1022 to 1024 range. This number is so large that it defies human comprehension. There are more stars in the observable universe than there are grains of sand on all the beaches and deserts of Earth combined. To put this cosmic inventory in perspective, consider that there are more stars in the observable universe than there are cells in all the humans who have ever lived on Earth. There are more stars than the total number of words ever spoken by our entire species throughout history. There are more stars than the number of snowflakes that have fallen on Earth in the past million years. These comparisons barely scratch the surface of conveying the true magnitude of stellar abundance in our cosmos. But even this staggering number of stars may represent only a tiny fraction of the total stellar population if the universe extends far beyond what we can observe. Recent observations from the James Webb Space Telescope have pushed our observational boundaries closer to the Big Bang than ever before, revealing mature galaxies that existed when the universe was only 300-400 million years old. These observations suggest that star and galaxy formation began earlier and proceeded more rapidly than previously thought possible. The James Webb Space Telescope, with its 6.5-meter primary mirror and advanced infrared capabilities, can observe light from the first galaxies that formed after the cosmic dark ages ended. These primordial galaxies appear as they were over 13 billion years ago, showing us cosmic history unfolding in reverse as we look deeper into space and further back in time. The most distant galaxy confirmed by JWST, designated JD's GS Z13-0, appears as it was just 325 million years after the Big Bang, when the universe was only 2.4% of its current age. These distant galaxies challenge our understanding of early cosmic evolution. They appear more massive and more mature than theoretical models predicted, suggesting that the first generation of stars formed from primordial hydrogen and helium processed this material through nuclear fusion, exploded as supernovae, and enriched their environments with heavy elements much faster than we thought possible. Some of these early galaxies already show signs of having supermassive black holes at their centers, another puzzle for theories of early cosmic evolution. The observable universe also contains the cosmic microwave background radiation, CMB, the afterglow of the Big Bang itself. This radiation fills all of space with a nearly uniform temperature of 2.7 Kelvin, above absolute zero, but tiny fluctuations, about 1 part in 100,000, tens to a few hundred microkelvin, reveal the quantum fluctuations that seeded all the structure we see in the universe today. The CMB represents a baby picture of the universe taken when it was only 380,000 years old, showing the cosmos at the moment it first became transparent to light. The patterns in the CMB fluctuations encode information about the fundamental parameters of our universe, its age, composition, geometry, and ultimate fate. Precise measurements of the CMB by satellites like WMAP and Planck have determined that the universe is 787 billion years old, is geometrically flat to within measurement precision, and consists of approximately 68.3% dark energy, 26.8% dark matter, and only 4.9% ordinary matter. This cosmic inventory reveals one of the most profound mysteries in all of science. We can directly observe and understand only about 5% of the universe. The remaining 95% consists of dark matter and dark energy, substances that interact with ordinary matter and energy only through gravitational effects. Dark matter provides the gravitational scaffolding that allowed ordinary matter to clump together and form stars and galaxies, while dark energy drives the accelerating expansion of space itself. The discovery of dark energy through observations of distant supernovae in the late 1990s revolutionized our understanding of cosmic evolution and the ultimate fate of the universe. These observations showed that the expansion of the universe is not slowing down due to gravitational attraction, as had been expected, but is actually accelerating. This acceleration appears to be driven by some form of energy inherent in space itself, what physicists call vacuum energy, or the cosmological constant. The implications of dark energy for the far future of the universe are profound and somewhat melancholy. The accelerating expansion means that galaxies beyond our local group are moving away from us at ever-increasing speeds. Eventually they will cross what cosmologists call the Hubble horizon, beyond which they recede faster than the speed of light due to the expansion of space itself. When this happens, we lose all causal contact with these distant regions. No signal, no matter how powerful, can bridge the gap created by accelerating expansion. In the far future, perhaps 100 billion years from now, galaxies beyond our local group will disappear beyond our cosmic horizon as space expands faster than light can travel between them. Future astronomers living in the merged Milky galaxy, the result of the Milky Way-Andromeda collision, will see a universe that appears to contain only their local galactic neighborhood, surrounded by empty darkness. The evidence for the Big Bang, the cosmic web, and the vast population of distant galaxies will have literally expanded out of sight. This means we live in a special epoch in cosmic history, when the universe is large enough to have formed complex structures like galaxies and stars, but not so old that cosmic expansion has erased the evidence of our cosmic origins. We exist in a brief window of cosmic time, perhaps the only window, when intelligent beings can observe and understand the full scale and history of their universe. The edge of the observable universe is also approaching us in a sense. As time passes, light from increasingly distant objects has more time to reach us, gradually expanding our cosmic horizon. Every second, our observable universe grows by 1 light second, about 186,082 miles, in all directions. Every year we can see about 1 light year farther into space, potentially revealing galaxies that were previously beyond our observational reach. However, this expansion of our observational horizon is more than offset by the acceleration of cosmic expansion. Galaxies that we can see today will eventually disappear from view, as they are carried beyond our cosmic horizon by the expansion of space. We are living in the golden age of cosmological observation, when the observable universe contains its maximum richness of structure and information about cosmic history. The boundary of the observable universe is not a physical edge or barrier, It's simply the limit of how far light has been able to travel since the universe became transparent. If we could somehow travel to what appears to be the edge of our observable universe, we would find more galaxies, more cosmic web structure, extending in all directions. The universe doesn't end at the boundary of what we can observe. That boundary simply moves with us, always maintaining a distance of 46, 5 billion light-years from our location. But here's where our journey takes its most mind-bending turn. The observable universe, vast as it is with its 93 billion light-year diameter and, likely, a few 100 billion galaxies, earlier extrapolations suggested up to per trillion, might represent just an infinitesimally small fraction of the actual universe. Beyond the boundary of what we can see, space almost certainly continues, possibly extending infinitely in all directions, populated by countless more galaxies, stars, and perhaps forms of matter and energy we cannot imagine. The question of what lies beyond our observable universe touches on some of the deepest mysteries in cosmology and philosophy. If the universe is truly infinite in extent, and many theoretical models suggest it is, then the implications are staggering and beautiful and terrifying all at once. An infinite universe would contain infinite matter and energy, infinite galaxies, and infinite possibilities for the arrangement and rearrangement of atoms and molecules. In an infinite universe, every possible configuration of matter that could exist within any given volume of space would not only exist somewhere, but would exist infinitely many times. This means that somewhere in the vast expanse beyond our cosmic horizon, there would be perfect copies of you, of Earth, of our entire local group, of our observable universe itself, repeated endlessly in an infinite cosmic symphony of variation and repetition. The mathematics of infinity suggest that in an infinite universe, there would be regions identical to our observable universe located at regular intervals throughout space. The distance to the nearest identical copy of our observable universe would be approximately 10, 10, 1, 15 light-years away, a number so large that it contains more digits than there are atoms in our observable universe. At such distances, even the concepts of distance and travel lose their conventional meaning, but the universe might be even stranger than simple infinity would suggest. The concept of cosmic inflation, strongly supported by observations of the cosmic microwave background radiation, proposes that our universe underwent a period of exponential expansion in its first fraction of a second. During this inflationary epoch, which lasted from about 10 joules to 36 seconds to 10 joules to 32 seconds after the Big Bang, space expanded by a factor of at least 10 to 26, possibly much more. This inflation could have stretched what was once a microscopic quantum fluctuation to a size vastly larger than what we can observe today, creating a universe that extends far beyond our cosmic horizon. Some speculative models of inflation suggest that our observable universe might be embedded within a universe enormously larger. Figures like a factor of 10 times 23 in linear dimension are illustrative rather than measured, making our observable patch proportionally smaller than a proton compared to a planetary system. If inflation proceeded to such extremes, a speculative extrapolation, the full universe could contain an astronomically large number of causally disconnected regions, sometimes rhetorically described with numbers like 1078 observable, universe-sized patches, each slightly different due to quantum fluctuations but all sharing the same physical laws and fundamental constants. The diversity of these regions would be bounded only by the laws of physics and quantum mechanics, creating a conceptual cosmic library of possible worlds consistent with our understanding of nature. But cosmic inflation might not have stopped everywhere at the same time. In many models of inflation, called eternal inflation, the process of exponential expansion continues in some regions while ending in others. This creates a fractal-like structure where inflating regions spawn new regions of space and time, each potentially with different physical properties and laws of nature. In eternal inflation models, our observable universe would be just one pocket universe within a vast, possibly infinite multiverse, containing countless other pocket universes, each with its own Big Bang, its own cosmic history, and potentially its own physical constants. Some of these pocket universes might have stronger or weaker gravitational forces, different numbers of spatial dimensions, or entirely different particles and fields than our own universe. The multiverse concept raises profound questions about the nature of physical law and the apparent fine-tuning of our universe for the existence of stars, planets, and life. In our universe, the fundamental constants of nature seem to be precisely calibrated to allow the formation of atoms, molecules, stars, and the complex chemistry necessary for biology. If the strong nuclear force was slightly weaker, atomic nuclei couldn't form. If it were slightly stronger, hydrogen would be rare and long-lived stars couldn't exist. In a multiverse containing regions with all possible values of physical constants, universes like ours, capable of supporting complexity and life, might be rare statistical flukes. Most regions might be sterile, dominated by black holes, or filled with exotic forms of matter that prevent the formation of stable structures. We might exist in one of the rare cosmic oases where the constants happen to align in a way that permits the emergence of consciousness and intelligence. This multiverse perspective transforms questions about cosmic fine-tuning from arguments about design to questions about probability and selection effects. In an infinite multiverse, even extremely unlikely configurations would occur infinitely often, and conscious observers could only find themselves in universes capable of supporting their existence. The apparent fine-tuning of our universe might simply reflect the fact that we necessarily observed the kind of universe that could produce observers. Some speculative analyses have searched the CMB for patterns that might be explained by hypothetical collisions between our universe and other bubble universes, but no convincing, widely accepted evidence has emerged. Claims of CMB bruises remain unconfirmed and controversial. The James Webb Space Telescope and other advanced observatories are pushing the boundaries of what we can observe ever closer to the edge of our cosmic horizon. While we cannot directly observe other universes or regions beyond our cosmic boundary, we might be able to detect their indirect effects through gravitational influences, cosmic background radiations, or other subtle signatures that cross the boundaries between different regions of the multiverse. But the scales we're discussing, infinite universes, eternal inflation, multiverses hypothetically containing astronomically large numbers of pocket universes, illustrative figures like 1078 are speculative rhetoric, begin to strain the very meaning of scientific inquiry. How do we test theories about regions of space we can never observe? How do we apply the scientific method to concepts that are, by definition, beyond the reach of empirical investigation? Some physicists argue that multiverse theories are not truly scientific because they make no testable predictions and cannot be falsified through observation. Others contend that these theories emerge naturally from well-tested physical principles like quantum mechanics and general relativity, and that the multiverse is a logical consequence of our best understanding of fundamental physics, even if we cannot directly observe its full extent. The philosophical implications of an infinite or near-infinite universe are as staggering as the scientific ones. In an infinite universe, every thought you've ever had would be thought by infinitely many beings throughout cosmic space. Every decision you've made would be made differently by infinitely many alternate versions of yourself in distant regions, where quantum events unfolded differently. The concept of cosmic infinity also raises questions about meaning, purpose, and uniqueness. If everything that can happen does happen infinitely often throughout an infinite universe, what makes any particular event or existence special? How do we find meaning in a cosmos where every possible story plays out infinitely many times across infinite space? Yet perhaps the very ability to contemplate these questions, to wonder about infinity, to seek meaning in the face of cosmic vastness, is itself what makes consciousness and intelligence remarkable phenomena in the universe. Even if we exist in one of infinitely many similar configurations, the subjective experience of wonder, discovery, and understanding remains precious and profound. The measurement of cosmic scale has also revealed deep connections between the very large and the very small. The cosmic microwave background fluctuations that seeded the formation of galaxy superclusters originated as quantum fluctuations smaller than a proton in the first moments after the Big Bang. The universe's largest structures trace their origins to its smallest quantum events, inflated by cosmic expansion to spans of hundreds of millions of light years. This connection between quantum mechanics and cosmic structure represents one of the most beautiful insights in modern physics. The uncertainty principle that governs subatomic particles also determines the statistical properties of galaxy distributions across billions of light years. The same mathematics that describes electron wave functions also describes the cosmic web of dark matter filaments that scaffold the observable universe. String theory and other attempts to unify quantum mechanics with gravity suggest that the fundamental structure of space-time itself might be discrete rather than continuous at the smallest scales. If space and time are quantized at the Planck length, about 10 to the 45 meters, and Planck time, about 10 to the 44 seconds, then even infinite space would contain only a finite, though unimaginably large, number of possible configurations within any given volume. These quantum aspects of spacetime would place subtle limits on the diversity possible in an infinite universe, creating a cosmic library that, while vast beyond comprehension, would still be bounded by the discrete nature of quantum reality. Even infinity, it seems, operates within constraints imposed by the fundamental laws of physics. The scales we're discussing truly begin to strain the very meaning of the word large. When we talk about a possibly infinite universe, or a multiverse containing infinite universes, or cosmic structures spanning hundreds of billions of light years, we've moved far beyond measurements that have any practical meaning for human experience. We've entered the realm where mathematics becomes the only language capable of describing reality, where numbers themselves become inadequate tools for conveying the true magnitude of cosmic existence. Consider the hierarchy of structures we've explored on our journey tonight, each step representing a leap in scale that challenges our evolved ability to comprehend spatial relationships. From Earth to our solar system represents an increase by a factor of about 1,000 in linear dimension. From our solar system to nearby stars multiplies the scale by another factor of about 10,000. From nearby stars to our galaxy, increases the scale by approximately 10 million. From our galaxy to nearby galaxies like Andromeda represents a relatively modest factor of about 25, but from nearby galaxies to galaxy clusters multiplies by roughly 100. From clusters to superclusters increases the scale by another factor of about 100, and from superclusters to the observable universe multiplies by about 1,000. Each step in this cosmic hierarchy represents a conceptual leap that our brains evolved to understand the scales relevant to survival on an African savanna over millions of years of evolution struggle to process. We developed intuitive understanding of distances we could walk, objects we could throw, territories we could defend, but never of light years or galactic superclusters or cosmic voids spanning hundreds of millions of years of light travel time. The fact that we can comprehend these scales at all, that beings barely 6 feet tall living on a world less than 8,000 miles across can measure structures spanning hundreds of billions of light years, represents perhaps the most remarkable achievement of human consciousness and scientific methodology. We have transcended the limitations of our biological heritage through the power of mathematics, careful observation, and logical reasoning. But understanding cosmic scale isn't just an academic exercise in large numbers and impressive distances. These measurements tell us profound truths about the nature of existence itself, about the conditions necessary for complexity and consciousness to emerge from cosmic evolution. The universe's vast size and immense age are intimately connected to the existence of stars, planets, chemistry, biology, and ultimately the emergence of beings capable of contemplating cosmic scale. Stars need billions of years to forge the heavy elements necessary for planets and life through nuclear fusion in their cores. The carbon in your body, the oxygen you breathe, the iron in your blood, the calcium in your bones, all of these elements were created in stellar interiors through processes that require millions or billions of years to complete. When massive stars reach the end of their lives and explode as supernovae, they scatter these elements throughout space, enriching the interstellar medium and making possible the formation of new generations of stars with planetary systems rich in the heavy elements essential for rocky worlds and biological chemistry. Galaxies need hundreds of millions of years to settle into stable structures capable of supporting long-lived stellar systems like our solar system. The early universe was a violent place, with frequent galaxy mergers and collisions that would have disrupted planetary systems and prevented the stable, long-term evolution necessary for the development of complex life. Our current cosmic epoch, roughly 8 billion years after the Big Bang, represents a relatively calm period when galactic evolution has produced stable environments where planetary systems can persist for billions of years. The enormous scale of space ensures that despite containing trillions of galaxies and uncountable numbers of stars, the universe is still mostly empty space. This cosmic emptiness isn't a waste of space. It's a necessary feature that allows structures to form and evolve without constant catastrophic interactions. If the universe were much smaller or much denser, gravity would have caused everything to collapse back together into black holes long ago, preventing the formation of stars and planets entirely. Conversely, if the universe were expanding much faster than it actually is, matter would be spread so thin that gravitational attraction could never overcome cosmic expansion to form stars, galaxies, and the complex structures we observe. The expansion rate of our universe falls within a narrow range that permits both the formation of cosmic structures and their long-term stability, a cosmic Goldilocks condition that appears to be essential for the emergence of complexity. The cosmic scale also reveals our profound cosmic solitude and connection simultaneously. We are separated from our nearest stellar neighbours by distances so vast that communication or travel remains practically impossible with any conceivable technology. The nearest star system, Alpha Centauri, lies 4.24 light-years away, a distance that would require over 70,000 years to traverse using our fastest current spacecraft. Even signals travelling at the speed of light would take over 8 years to make a round trip to our nearest stellar neighbours. This cosmic isolation means that if intelligent life exists elsewhere in our galaxy, civilizations might be separated by such vast distances and timescales that meaningful communication or interaction becomes nearly impossible. The Drake equation, which attempts to estimate the number of communicating civilizations in our galaxy, includes factors for the formation rate of stars, the fraction with planets, the fraction where life develops, and the fraction where intelligent life evolves. But it also includes the crucial factor of how long such civilizations persist. If most technological civilizations destroy themselves or fade away within a few centuries or millennia, they would exist in isolation from one another across space and time. Yet despite this cosmic loneliness, we are all profoundly connected through the cosmic web of space and time, through shared origins in the Big Bang, and through the recycling of elements forged in stellar cores throughout cosmic history. Every atom in your body was once part of a star that lived and died billions of years ago. The calcium in your teeth was forged in the nuclear furnace of a massive star that exploded as a supernova, scattering its elements through space where they were eventually incorporated into the molecular cloud that collapsed to form our solar system. The hydrogen atoms in your body, which make up about 60% of your atomic composition, are even more ancient. They were created not in stellar cores, but in the first few minutes after the Big Bang itself, during a period called Big Bang nucleosynthesis, when the entire universe was hot and dense enough to fuse protons into heavier elements. Every hydrogen atom in your body has existed for 8 billion years, witnessing the entire cosmic story from the formation of the first atoms to the emergence of consciousness capable of contemplating cosmic origins. We are not separate from the universe. We are the universe becoming conscious of itself, a temporary arrangement of stardust that has somehow acquired the ability to wonder at its own cosmic heritage. This perspective fundamentally transforms how we think about our relationship to the cosmos. We are not alien visitors or accidental passengers on a hostile world hurtling through empty space. We are an integral part of cosmic evolution, as natural and inevitable as stars, galaxies, and planets themselves. The measurement of cosmic scale has also revealed that the universe is not only vast but profoundly dynamic and evolving. Space itself is expanding, carrying galaxies away from each other at ever-increasing speeds due to the influence of dark energy. This expansion, first discovered by Edwin Hubble in the 1920s through observations of distant galaxies, means that the universe was smaller in the past and will be larger in the future. The cosmos is not a static stage upon which cosmic events unfold, but a dynamic, evolving entity that changes on the grandest possible scales. The expansion of the universe allows us to look backward in cosmic time simply by observing distant objects. Light from nearby galaxies shows us the cosmos as it was millions of years ago. Light from distant galaxy clusters reveals cosmic history from billions of years in the past. The most distant observations show us the universe as it was when the first stars and galaxies were forming, allowing us to witness cosmic evolution unfolding across space and time. This connection between distance and cosmic time, where looking farther into space means looking deeper into the past, has revealed that the universe has undergone dramatic changes throughout its history. The early universe was smaller, hotter, denser, and more uniform than today. It contained no stars, no heavy elements, no planets, and no possibility for the complex chemistry that underlies biology. The cosmic structures we observe today, galaxies, stars, planets, and ultimately life itself, are products of billions of years of cosmic evolution. The discovery of dark energy through observations of distant supernovae has revealed that our universe's expansion is accelerating, driven by some form of energy intrinsic to space itself. This acceleration means that the universe will continue expanding forever, carrying distant galaxies beyond our cosmic horizon as space expands faster than light can travel between widely separated regions. In the far future, perhaps 100 trillion years from now, the last stars will burn out as the universe becomes too dilute to support further star formation. Galaxies will fade as their stellar populations age and die. Even protons might decay, causing atoms themselves to disintegrate over timescales so vast that they dwarf the current age of the universe by incomprehensible factors. The universe might end as a cold, dark, nearly empty expanse of space, containing only black holes slowly evaporating through Hawking radiation over periods measured in 1,000 years or more. Yet this distant future cosmic fate should not diminish the wonder and meaning we find in our current cosmic epoch. We exist during a remarkable period in cosmic history, when the universe is large enough to contain billions of galaxies and countless stars, yet young enough that stellar evolution has not yet extinguished the nuclear fires that power cosmic illumination. We live in an age when intelligent beings can observe and understand the cosmic story, when consciousness can contemplate its own cosmic origins and destiny. The measurement of cosmic scale has revealed deep connections between the physics of the very small and the very large, between quantum mechanics and cosmic structure formation. The tiny quantum fluctuations that existed in the first moments after the Big Bang, amplified by cosmic inflation, seeded the formation of all the structures we observe today, from galaxy superclusters spanning hundreds of millions of light years to the cosmic web that organizes matter on the largest observable scales. This quantum-to-cosmic connection demonstrates the profound unity underlying natural phenomena. The same physical principles that govern the behavior of subatomic particles also determine the statistical properties of galaxy distributions across billions of light years. The mathematics of quantum field theory finds application in cosmology, while observations of cosmic structure test theories originally developed to describe the microscopic world. Recent observations have pushed our understanding of cosmic scale to its very limits, revealing structures and phenomena that challenge our theoretical models and expand our conception of what's possible in the universe. The James Webb Space Telescope, with its unprecedented infrared sensitivity and resolution, has observed galaxies that existed when the universe was only 300–400 million years old, showing us cosmic history closer to the Big Bang than ever before achieved. These early galaxies appear surprisingly massive and mature for their age, suggesting that the process of structure formation proceeded much more rapidly in the early universe than our current models predict. Some of these primordial galaxies already show evidence of supermassive black holes at their centers, raising profound questions about how such massive objects could form so early in cosmic history when there hadn't been sufficient time for the conventional process of black hole growth through accretion. The Hubble Space Telescope has also contributed to our understanding of cosmic scale through its deep field observations, which have revealed galaxies at distances approaching the edge of the observable universe. The Hubble Ultra Deep Field, created by pointing the telescope at a tiny patch of apparently empty sky for hundreds of hours, revealed over 10,000 galaxies in a region of space smaller than a grain of sand held at arm's length. This observation demonstrated that virtually every direction we look in space contains countless galaxies, extending to the very limits of our observational capabilities. We've also discovered that some reported large-scale features in galaxy surveys appear to approach or exceed heuristic expectations for structure size in our current cosmological model. The Hercules Corona Borealis Great Wall, an assemblage of gamma-ray burst positions and inferred large-scale clustering cited as spanning several billion light-years, has been described as one of the largest apparent structures, though its reality, exact extent, and statistical interpretation are debated and may be influenced by survey selection effects. Such claims motivate continued scrutiny of cosmic homogeneity and the processes that govern structure formation on the largest scales. Discussion of these candidate enormous features has led to debates about whether the universe is as homogeneous and isotropic, the same in all directions, as the standard cosmological model assumes. The cosmological principle, statistical sameness on sufficiently large scales, remains broadly supported, though objects like the reported Hercules Corona Borealis Great Wall highlight the importance of testing for survey biases and statistical anomalies at the frontier of current datasets. The measurement of cosmic distances relies on what astronomers call the cosmic distance ladder, a series of overlapping measurement techniques that allow us to gauge distances from nearby stars to the edge of the observable universe. This ladder begins with parallax measurements of nearby stars, where we use Earth's orbital motion around the Sun to create a baseline for triangulation. For stars within about 100 light-years, this geometric method provides direct, reliable distance measurements. Beyond the reach of parallax measurements, astronomers use standard candles, objects whose intrinsic brightness is known or can be calibrated. Cepheid variable stars, whose pulsation periods are directly related to their luminosity, serve as standard candles for distances up to about 100 million light-years. For even greater distances, Type Ia supernovae, which have remarkably consistent peak brightnesses, can be observed across billions of light-years and provide the primary means of measuring distances to the most remote galaxies. Each rung of this distance ladder has its own uncertainties and systematic errors, and these uncertainties compound as we measure ever greater distances. This means that while we can confidently say the observable universe is approximately 93 billion light-years in diameter, the exact value carries significant uncertainty. The scale of the universe beyond what we can observe remains completely unknown, and possibly unknowable through direct observation. The cosmic distance ladder has also revealed one of the most perplexing problems in modern cosmology: the Hubble tension. Different methods of measuring the universe's expansion rate yield slightly different values, suggesting either that our understanding of cosmic evolution is incomplete, or that there are systematic errors in our distance measurements. This discrepancy might seem small, a difference of about 10% in the measured expansion rate, but it has profound implications for our understanding of cosmic scale and evolution. If the higher measurements of the Hubble constant are correct, the universe is expanding faster than predicted by our standard cosmological model, which could require new physics beyond what we currently understand. Alternatively, if systematic errors in distance measurements are responsible for the discrepancy, it would highlight the challenges inherent in measuring cosmic scales with high precision across billions of light years. The question of cosmic scale intersects with some of the deepest questions in physics and philosophy. If the universe is infinite in extent, as many theoretical models suggest, it raises profound questions about the nature of physical law, causality, and the meaning of individual existence. In an infinite universe, every possible configuration of matter would exist infinitely many times, including perfect copies of you, Earth, and our entire observable region of space. This possibility challenges our concepts of uniqueness and identity. If infinite versions of you exist throughout an infinite cosmos, which one is the real you? How do we assign meaning or significance to events and choices if every possible alternative also occurs infinitely often elsewhere in space? These questions push us beyond the boundaries of science into the realms of philosophy and metaphysics. The scale of our universe also raises profound questions about the likelihood and distribution of life elsewhere in the cosmos. With trillions of galaxies, each containing billions of stars, and many of those stars hosting planetary systems, the sheer number of potentially habitable worlds is staggering. The Drake equation attempts to estimate the number of communicating civilizations in our galaxy alone, yielding results that range from "we are alone" to millions of civilizations exist. Yet the vast distances between stars mean that even if life is common throughout the universe, civilizations may be isolated by gulfs of space and time too large to bridge with any conceivable technology. The nearest potentially habitable exoplanet, Proxima Centauri b, lies 4.24 light-years away, a distance that would require thousands of years to traverse using our most advanced propulsion technologies. Even radio signals traveling at the speed of light would take over 8 years to make a round trip to our nearest stellar neighbor. This cosmic isolation might be a universal phenomenon. If most technological civilizations are separated by hundreds or thousands of light years, the timescales for communication or interaction would exceed the typical lifespans of civilizations themselves. The universe might be teeming with life, yet each civilization might experience the cosmos as an empty, silent expanse due to the sheer scale of space and the limitations imposed by the speed of light. The cosmic perspective fundamentally changes how we think about ourselves and our place in existence. We are not the center of creation, as our ancestors believed for thousands of years. We're not even residents of a typical galaxy in a typical region of space. We exist in one small corner of what may be an infinite cosmos, on a tiny planet orbiting an ordinary star, constructed from atoms forged in the deaths of earlier generations of stars that lived and died billions of years before our solar system formed. Yet this cosmic perspective, while humbling, is also profoundly empowering and meaningful. Despite our infinitesimal size compared to cosmic structures, despite our brief existence compared to cosmic timescales, we have managed to measure the universe from the quantum scale to the cosmic horizon. We've traced our cosmic address from Earth to the local group, to the Virgo supercluster, to Laniakea, to the cosmic web, to the edge of the observable universe and beyond, to the theoretical possibility of infinite space itself. The tools we use to measure cosmic scale, telescopes, spectrometers, computers, mathematical equations, are built from the same atoms that were forged in stellar cores billions of years ago. The consciousness that contemplates cosmic infinity emerge from the same cosmic processes that created galaxies, stars, and the complex chemistry that underlies all biological phenomena. We are not separate observers of the universe. We are the universe observing itself, measuring itself, coming to understand its own vast scale and magnificent complexity. This realization transforms our understanding of what it means to exist. We are temporary patterns in the cosmic flow of matter and energy, brief arrangements of stardust that have somehow acquired the capacity for wonder, for measurement, for love, and for understanding. In a cosmos where galaxies are separated by millions of light years and stars burn for billions of years, human consciousness represents something genuinely extraordinary, perhaps the rarest and most precious phenomenon in the entire universe. The emergence of intelligence and consciousness from cosmic evolution suggests that the universe has an inherent tendency toward increasing complexity and organization. From the simple hydrogen and helium forged in the Big Bang, cosmic processes have created the entire periodic table of elements, complex molecules, planetary systems, and ultimately biological systems capable of reproduction, evolution, and conscious thought. This cosmic evolution from simplicity to complexity appears to violate the second law of thermodynamics, which states that entropy, disorder, should increase over time. However, the universe as a whole does indeed become more disordered as it expands and cools. But local regions can become highly organized through processes that dissipate energy into their surroundings. Stars, planets, life, and consciousness are all examples of local decreases in entropy made possible by the overall cosmic trend toward increasing disorder. In this sense, we exist as temporary islands of order and complexity in a universe inexorably trending toward maximum entropy and heat death. Yet rather than making our existence meaningless, this cosmic context makes consciousness and intelligence even more remarkable. We represent the universe's attempt to understand itself, to create meaning and beauty and purpose within the constraints imposed by physical law and cosmic evolution. As we conclude this journey through cosmic scale, let us return to where we began, but with a transformed understanding of our place in existence. You are still sitting where you were when we started this exploration, perhaps in the same chair, in the same room, on the same planet. Yet now you carry within your mind a map of the universe that spans from quantum fluctuations smaller than protons to structures larger than hundreds of billions of light years, from moments after the Big Bang to the distant future when the last stars will fade into darkness. The room around you suddenly takes on new meaning when viewed through the lens of cosmic scale. The air you breathe contains atoms that have travelled across the galaxy, having been forged in stellar cores that burned for billions of years before our solar system existed. The light illuminating your space carries photons that began their journey in the nuclear furnace of our sun, having taken tens of thousands of years to work their way from the solar core to the surface, before racing across 93 million miles in just over 8 minutes to reach your eyes. Your body itself is a collection of roughly 37 trillion cells, each containing the genetic information necessary to construct a conscious being capable of contemplating infinity. The calcium strengthening your bones was created in the core of a massive star that exploded as a supernova, scattering its elements across hundreds of light years of space. The iron carrying oxygen through your bloodstream was forged in the final moments of stellar collapse, when temperatures and pressures reached conditions that existed nowhere else in the universe except in the cores of dying stars. The carbon atoms forming the backbone of every organic molecule in your body were manufactured through the triple alpha process in stellar interiors, where 3 helium nuclei combine in a perfectly choreographed cosmic dance that requires temperatures of over 100 million degrees Celsius. Without this precise nuclear process, discovered and understood through decades of careful observation and theoretical work, complex chemistry and life as we know it could not exist. But you are more than just a collection of stellar remnants. You are the universe becoming conscious of itself, a temporary arrangement of matter and energy that has somehow acquired the capacity for wonder, for scientific inquiry, for love, and for meaning-making. In a cosmos where most matter exists as plasma in stellar cores or as cold dust in interstellar space, the complex chemistry of biological systems represents something genuinely extraordinary. The human brain contains approximately 86 billion neurons, each connected to thousands of others, creating a network of computational complexity that rivals or exceeds the most sophisticated artificial intelligence systems we can construct. This biological computer, powered by about 20 watts of energy, less than a bright light bulb, can contemplate the infinite, solve equations describing cosmic evolution, and create art, music, and literature that capture the beauty and meaning of existence. Your consciousness, reading these words and contemplating cosmic scale, represents perhaps the rarest phenomenon in the entire universe. While stars, planets, and even complex molecules might be relatively common throughout the cosmos, the emergence of self-aware beings capable of scientific thought and cosmic contemplation might be extraordinarily rare. You might be participating in one of the universe's rarest and most precious activities, conscious reflection on the nature and scale of existence itself. The cosmic perspective we've explored tonight transforms not only how we see the universe, but how we understand our responsibilities to each other and to the planet that gave rise to consciousness. If we are indeed rare in the cosmos, if conscious intelligence represents one of the universe's most remarkable achievements, then every human mind becomes precious beyond measure, a unique lens through which the universe can observe and understand itself. This cosmic perspective dissolves many of the artificial boundaries and divisions that separate human beings from one another. Viewed from the distances of nearby stars, national borders vanish entirely. From the scale of our galaxy, our entire planet becomes invisible. All human conflicts, all the political and religious divisions that seem so important in daily life, fade into insignificance when measured against the vast scales of space and time that define our cosmic environment. Yet this perspective also emphasizes the profound connections that bind us together. Every person you encounter is made from the same stellar material, shares the same cosmic heritage, and participates in the same extraordinary phenomenon of consciousness emerging from cosmic evolution. The genetic differences that separate human populations are trivial compared to what we share. A common origin in African evolutionary history, a common inheritance of stellar elements, and a common capacity for wonder at the universe that contains us. The cosmic scale we've explored also provides perspective on the challenges facing human civilization. Climate change, resource depletion, political conflicts, and social inequalities are real and urgent problems that demand immediate attention and action. But viewed against the backdrop of cosmic evolution, these challenges represent opportunities for our species to demonstrate the same problem-solving capabilities that allowed us to discover our cosmic address and measure the universe itself. We are the first generation of humans to understand our true place in the cosmic hierarchy, to map the universe from its smallest to largest scales, and to trace our heritage back to the Big Bang itself. This knowledge brings with it both humility about our cosmic insignificance and pride in our remarkable achievements in understanding. We exist for less than a cosmic instant on a world smaller than a grain of sand compared to cosmic scales. Yet we have managed to comprehend the universe that contains us. The measurement of cosmic scale continues to push the boundaries of human knowledge and technological capability. The James Webb Space Telescope is revealing galaxies that formed when the universe was younger than 5% of its current age. The Event Horizon Telescope has imaged the shadows of black holes billions of times more massive than our Sun. Gravitational wave detectors are listening to the cosmic vibrations created by colliding black holes and neutron stars across billions of light-years of space. Future observatories will push our cosmic vision even further, possibly detecting the first stars that formed in the universe, mapping the cosmic web in unprecedented detail, and perhaps even finding evidence for other universes beyond our own. The Vera C. Rubin Observatory will survey the entire visible sky every few nights, creating a movie of the cosmos that reveals how structures form and evolve over cosmic time. The extremely large telescope, when completed, will have a primary mirror 39 meters across, providing resolution sharp enough to observe potentially habitable exoplanets around nearby stars. These advancing capabilities will refine our measurements of cosmic scale, and perhaps resolve some of the current mysteries about the universe's size, age, and ultimate fate. They might also reveal new mysteries that we haven't yet imagined, reminding us that the universe consistently surprises us with phenomena beyond our current theoretical understanding. The question of whether we are alone in the universe may finally be answered in the coming decades. The discovery of thousands of exoplanets has revealed that planetary systems are common around other stars, and many of these worlds lie within the habitable zones where liquid water could exist on their surfaces. Future telescopes will be capable of analyzing the atmospheres of these distant worlds, searching for the chemical signatures that might indicate biological activity. The discovery of life elsewhere in the universe would provide a new perspective on cosmic scale and our place within it. If life proves to be common throughout the cosmos, it would suggest that the emergence of complexity and consciousness might be natural outcomes of cosmic evolution. If we remain the only known example of life and intelligence, it would emphasize the precious and possibly unique nature of our existence. But regardless of whether we are alone or part of a universe teeming with life, the cosmic scale we've explored tonight reveals that we exist in a magnificent cosmos that stretches from the quantum realm to possibly infinite space, from the first moments after the Big Bang to a far future that extends trillions of years beyond our current epoch. We are part of a cosmic story that is still being written, participants in an ongoing process of evolution and complexity that might be occurring throughout the universe. The night sky above you contains roughly 2,500 stars visible to the naked eye under perfect dark conditions, each representing a sun potentially like our own, many hosting planets, and possibly even life. But those visible stars are just our immediate stellar neighborhood, a tiny sample of the 200–400 billion stars in our galaxy alone. And our galaxy is just one of perhaps a few 100 billion galaxies, earlier extrapolations suggested up to 2 trillion, in the observable universe, each containing its own populations of stars, planets, and possibilities. When you look up at the stars tonight, remember that you are seeing both vast distances and deep time. The light from Sirius, the brightest star in the night sky, left that star 8.6 years ago and has been travelling toward Earth at 186,282 miles per second ever since. The light from the stars in the constellation Orion left those stellar systems between 200 and 2000 years ago, carrying information about cosmic conditions that existed during the height of the Roman Empire or the European Middle Ages. The faint band of the Milky Way visible on dark nights represents our edge-on view of our own galaxy, containing the combined light of billions of stars too distant to resolve individually. When you see the Milky Way stretching across the sky, you are looking toward the center of our galaxy, seeing light that has travelled thousands of light years from stars that orbit the supermassive black hole at our galactic core. But even the most distant objects visible to the naked eye represent just the beginning of cosmic scale. The Andromeda Galaxy, visible as a faint smudge in the constellation Andromeda, appears as it was 2.5 million years ago, when our human ancestors were just beginning to use stone tools. The light you see from Andromeda began its journey long before our species existed in recognizable form. The cosmic microwave background radiation, detectable only with sensitive radio telescopes but surrounding us in all directions, carries information about the universe when it was only 380,000 years old, less than 3% of its current age. This radiation has been travelling toward us for 13.8 billion years, carrying the imprint of quantum fluctuations that seeded all the cosmic structures we observe today. In the quiet moments that follow our cosmic journey, whether you're watching the sunset paint the sky in colours created by light, scattering through our planet's atmosphere, or gazing up at stars whose light has travelled for years or centuries to reach your eyes, remember that you carry within yourself the capacity to contemplate infinity. The universe may be beyond all measure, but your ability to wonder at its scale, to find beauty in its vastness, and to discover meaning in its magnificent complexity, that is perhaps the most extraordinary fact of all. You are small in cosmic terms, occupying a volume of space that is negligible compared to stellar systems, invisible compared to galactic scales, and infinitesimal compared to the cosmic web that spans the observable universe. You exist for a brief moment in cosmic time, a lifespan that is microscopic compared to stellar evolution, instantaneous compared to galactic orbital periods, and essentially zero compared to the age of the universe itself. But you're also profound beyond measure. You're a pattern of consciousness that can contemplate the infinite, a temporary arrangement of atoms that can understand cosmic evolution, a fleeting biological system that can measure distances across billions of light years and times spanning billions of years. You contain within your mind a model of the universe that extends from quantum scales to cosmic horizons, from the Big Bang to the heat death of the cosmos. You are brief, but you're also eternal, connected to the cosmic story that began 13.8 billion years ago and will continue for trillions of years to come. The atoms in your body will persist long after your consciousness fades, eventually being recycled into new stars, new planets, and possibly new forms of complexity and awareness. You are a temporary manifestation of the universe's capacity for self-understanding, but your participation in cosmic contemplation connects you to the eternal processes of cosmic evolution. This is the true scale of our universe, not just its vast physical dimensions spanning billions of light years and trillions of galaxies, but its incredible ability to create beings capable of wonder, of measurement, of love, and of understanding. In a cosmos of potentially infinite scale, consciousness represents something genuinely special. The universe's way of knowing itself, of experiencing its own beauty, and of finding meaning in its own magnificent existence. As you rest now in the gentle embrace of cosmic perspective, surrounded by the familiar objects of your daily life but carrying within your mind a map of infinity, remember that you are both infinitesimally small and uniquely precious, both temporary and eternal, both separate and connected to everything that exists across the vast scales of space and time. The universe is vast beyond all imagination, filled with structures that dwarf our comprehension and scales that strain the meaning of our largest numbers. But it has produced you, and through you, it experiences wonder at its own infinite scale. You are not just in the universe. You are how the universe knows itself, measures itself, and finds meaning in its own boundless existence. Sleep well, cosmic wanderer. You are home in the infinite universe, and the infinite universe is home in you. Tomorrow, when you wake, you will still be a temporary arrangement of stellar material on a small planet orbiting an ordinary star in an unremarkable galaxy. But you will also be a conscious being capable of contemplating cosmic infinity, a remarkable achievement in a universe that spent nearly 14 billion years creating the conditions necessary for consciousness to emerge and wonder at its own magnificent scale. The cosmos is vast and you are small, but you are also aware, and that makes all the difference in a universe that might otherwise be nothing more than an unconscious arrangement of matter and energy, expanding through space and time. Through you, the universe becomes conscious of its own infinite beauty, its own staggering complexity, and its own remarkable capacity to create beings capable of understanding, of wonder, and of love. This is your cosmic inheritance, your place in the infinite hierarchy of scale that defines existence itself. From the quantum foam to the cosmic web, from the first moments after creation to the far future, when the last stars fade into darkness, you are part of it all, carrying within your consciousness the universe's own capacity for self-reflection and self-understanding. Welcome home to infinity, fellow traveller. The universe is vast, and so are you.